In this video, we're going to be looking at lesson 7.5 on using proportional relationships. The essential questions that we'll answer are how do you use ratios to make indirect measurements, and how to use scale drawings to solve problems. Here's some important vocabulary for this lesson. Our first word is indirect measurement, and that is any method that uses formulas, similar figures, and or proportions to measure an object. This chapter, we've been focusing a lot on similar figures and proportions. So when we do our indirect measurement today, we're going to be looking for similar figures and then setting up a proportion. Our second vocab word is a scale drawing. You've seen scale drawings probably before when you've looked at the directions for things. A scale drawing is a drawing of an object that is either smaller or larger than the object's actual size. A classic example of a scale drawing is a map. So when we look at a map, let's say a map of Cottage Grove, there's going to be a scale on that map, and the scale is a ratio of any length in the drawing to the actual length. So if I was to look at a map of Cottage Grove or something, we'd probably have a scale something like 1 centimeter corresponds to 2 miles. Or something like that. And that means that 1 centimeter on my map corresponds with 2 miles in real life. One way that we can measure objects indirectly is to compare shadows. A shadow of an object is going to be proportional to the object's height. So in sunlight, a cactus casts a shadow that's 9 feet. And you can see in my picture, the 9-foot shadow, the shadow always goes on the ground. So that's the shadow of the cactus. At the same time, a person 6 feet tall casts a 4-foot shadow. Use similar triangles to find the height of the cactus. Now, before I set up my proportion to find the height of the cactus, I want to just briefly touch on why these two triangles are similar. First, the person and the cactus are both going to be perpendicular to the ground. So these are right triangles, so that's one angle. Another angle that we can show is the same is this angle right here. I'm going to call that angle 1. And this angle right here, I'll call that angle 2. Angle 1 is going to be congruent to angle 2 in my pictures because the sun's rays are parallel. So what do we mean by that? Well, let's just put a sun up in the sky here. So the sun's up here somewhere, and the sun has its rays. So let's say this is the rays of the sun's rays. Well, these triangles eventually are going to extend and hit up here. Right, and the angle it hits here and the angle it hits there are congruent. So angle 1 and angle 2 are going to be congruent as well because of the alternate interior angles. Now, you don't really need to understand that to understand this problem. You really just need to recognize that the triangles are similar because the angle to the sun is the same and the 90-degree angle is the same. So what I really want to do now is I want to set up a proportion. And as we've seen throughout this chapter, there's more than one way to do it. I like to compare the height to the height. So let's go with the person's height over the cactus height. So I'm going from left to right, person to cactus, and that's going to be equal to the ratio of the person's shadow to that of the cactus shadow. So I'm going kind of left to right. So setting up our proportion, if we fill in those values, we would have person's height, 6 feet, over X feet. We don't know how tall the cactus is. And that's going to be equal to person's shadow, which is 4 feet, and the cactus shadow, which is 9 feet. Now it's a proportion, and we can just use our cross products to get the answer. So 6 times 9 has to equal x times 4. That's 54 equals 4x. And then if we divide by 4 on each side, 54 divided by 4 is 13.5. So 13.5, again, was the height of the cactus. So I'm going to say the cactus is 13.5 feet tall. So I'm going to just write a short sentence. The cactus is 13.5 feet tall. At minimum, you need to include the unit. So if I wanted to skip writing the sentence and just write 13.5 feet, that would be fine as well. This next example also involves using shadows for indirect measurement. Here, a student wants to find the height of a statue of a pineapple in Nabur, Australia. She measured the pineapple shadow and her own shadow. The student's height is 5 feet 4 inches. Let's go ahead and add that 5 feet 4 inches to our diagram. So 5 feet 4 inches. And we want to know, what is the height of the pineapple? So the height of the pineapple, I'm going to put an X there. Now, what we need to notice here that makes this problem more challenging is 5 feet 4 inches. Like, there's no way to put that in the calculator. So we need to make sure that we start by converting units. So I'm going to convert all my units to inches. And you probably recall that 1 foot is equal to 12 inches. So let's go ahead and take all the numbers that have feet in them and convert them to inches. I'm going to start with the person. The person is AE in the picture right here. They are 5 feet 4 inches. And a foot is 12 inches. So if we take 5 times 12, that's inches. And then we add another 4 inches to it. 5 times 12 is 60. Add 4. We have 64 inches for the person. So that's the number that we're going to use when we make our calculation, 64 inches. Let's do the same with the person's shadow. The person's shadow, BC, is equal to 2 feet. And again, there are 12 inches in a foot. So if we take 2 times 12, that's 24 inches. Let's make one more conversion here for the pineapple's shadow. That's EF in the picture, and you can see that EF is 8 feet 9 inches. 8 feet would be 8 times 12 inches. That covers the 8 feet. Then we have to add on 9 more inches. And if you calculate that out, it ends up being 105. So the shadow of the pineapple is 105 inches. And now we just need to figure out how many inches tall is our pineapple. So the second step, now that we've made our conversions, is to set up and solve a proportion. So set up and solve a proportion. And there's a lot of different ways that we can write our proportion. As long as we follow the same pattern each time, it'll work. I like to just go like height to height and shadow to shadow. So I'm going to go kind of from left to right here. Let's see if we can find a color that shows up better. Let's go red. So I have 64 inches over X inches. The top is the person, and the bottom is the pineapple. Well, if I go the same pattern now, but with the shadows, the person's shadow is 24 inches there on the top, And the pineapple shadow is 105 inches. That's the bottom. Notice I went the same direction each time, left to right. 64 over x equals 24 over 105. And now we can go ahead and just solve that with a cross product. 64 times 105 has to equal x times 24. Take your calculator and multiply that out. You'll get 6,720 equals 24x. And then if we just divide by 24, we are going to get x equals 280. I should include a unit in my final answer. So our pineapple is 280 inches. For our next example, we're going to move to scale drawing applications, and one great application of a scale drawing is a map. The scale on the map of downtown Dallas is 1.5 centimeters to 300 meters. Now remember that the colon is the fraction bar. So this means our scale is 1.5 centimeters over 300 meters. And I would recommend that you leave the units in there to help you do the matching game. That scale means that for every 1.5 centimeters on the map, it represents 300 meters in the real downtown Dallas. Well, we want to know that if the distance between Union Station and the Dallas Public Library is 6 centimeters on the map, find the actual distance between the two buildings. Well, the 6 centimeters is going to match up with the 1.5 centimeters, and then the actual distance between the buildings is going to be some value x, and then it's in meters. So notice I've kind of played the matching game here. I have my units lined up, centimeter, centimeter, and then meter and meter. So now we can go ahead and just do our cross products. So that's 1.5 times x equals 300 times 6. And here I don't need to do any conversions of my units because we can enter 1.5 and 300 into our calculator. We only switched units on the pineapple problem because there was no way to enter something like 8 feet 9 inches into our calculator. Here, 1.5 and 300 are just fine. So I have 1.5x, and that is going to be equal to 300 times 6, which is 1,800. And then we'll divide by 1.5 to get our answer of 1,200. Make sure that you include a unit in your answer. So that's going to be 1,200, and then it's in meters for the actual distance. Problem B is exactly like the one we just did, except this time, the distance between City Hall and El Centro College is 4.5 centimeters. Let's find the actual distance between those buildings. It's the same scale as the problem we just completed, which was 1.5 centimeters to 300 meters. And this time on the map, we have 4.5 centimeters. That's going to correspond with some actual distance x in meters. Let's go ahead and do our cross products. 1.5 times x equals 300 times 4.5. We'll grab our calculators to get 1.5x equals 1,350. Divide by 1.5. And that'll give us our answer. It is 900. So the actual distance between these buildings is 900 meters. For our next example, we are going to... Here's one more example involving a scale drawing. And this time, we're given the actual dimensions of an object, and we want to make a scale drawing with a scale given. So let's just start by kind of visualizing this. The real Lincoln Memorial in Washington, D.C. is 57 meters long. So 57 meters long, that's the length, and 36 meters wide. So I'll just have that be the width. So I have a rectangle. Okay, if you made a scale drawing using the scale 1 centimeter to 15 meters, what would the dimensions of the drawing be? What we need to do here, because there are 2 dimensions, is we need to write and solve 2 different proportions. One for the length and one for the width. So you're going to do this problem in the exact same way that we just did A and B. We're going to start by writing down our scale, 1 centimeter to 15 meters, and then I'm going to play the matching game. So in real life, it's 57 meters long. Meters is on the bottom of my scale, so I'm going to line that up there. And then we want to know how many centimeters will the drawing be. So this is my lengths. Now we can just go ahead and do our cross products. 1 times 57 equals 15 times x. That's 57 equals 15x. Divide by 15. And when you put that into your calculator, it is 3.8. So 3.8 is my x, and my x corresponds with the length. So my length is 3.8. Let's go ahead and do a second proportion to find the widths. It's still the same scale factor. 1 centimeter corresponds with 15 meters. And the real Lincoln Memorial is 36 meters wide. So I'm going to line that up with the other meters. And then let's go ahead once again and solve this with a cross product. 1 times 36 is 36. 15 times x is 15x. We'll just divide by 15. And that will give us 2.4. So that, remember, is the width. So the width is 2.4. Let's just, for our final answer, let's make sure that we add the dimensions. So what would the dimensions of the drawing be? Well, the drawing is, and here's my 2 dimensions, 3.8 long, 2.4 wide. Remember, the drawings are in centimeters. So we can say something like the drawing is 3.8 centimeters long and 2.4 centimeters wide. For our final example, we're going to look at the proportional relationships between the perimeters and areas of similar figures. There's an example provided in your notes and right here on the screen that gives us 2 triangles that are similar. Triangle ABC is similar to triangle DEF. The similarity ratio is just the ratio of the sides. So we could technically pick any corresponding sides. In here, I have AB is 5 and DE is 10. Well, 5 over 10 is going to reduce to 1/2. So that's where the similarity ratio comes from. Now, if we calculate the perimeters, the perimeter of that first triangle, the smaller one, 4 plus 5 plus 3 is 12. And the perimeter of DEF, the bigger one, 10 plus 8 plus 6 is 24. Notice that these match. So the similarity ratio and the perimeter ratio are the same. The area ratio, though, is going to be a little bit different. And that's because area is a length times a length. And if I multiply by 1/2 twice, 1/2 times 1/2 is actually 1/4. So it's the similarity ratio squared. So in general, if the similarity ratio of 2 similar figures is A over B, then the ratio of the perimeters is going to be the same. The perimeter ratio and the similarity ratio are the same, both A over B. But for the ratio of the areas, that's going to be A divided by B, quantity squared. So if I'm trying to find a missing area, I'm going to have to take my similarity ratio and square it. And by the way, you square both the numerator and the denominator of your fraction. So let's go ahead and try an example. We're given here that triangle RST is similar to triangle UVW, and we want to find the perimeter and area of triangle UVW. The first step is to find the similarity ratio. And notice that RS and UV are in the same spot. So the similarity ratio, RS over UV, is equal to 16 over 20. And then we need to reduce the fraction. You can do it by hand by dividing by 4, or you can use the fraction button on your calculator and it will give you 4/5. So that 4 over 5 there is our similarity ratio. So the perimeter ratio is going to be the same as the similarity ratio. So my perimeter ratio is going to be 4:5, where 4 corresponds again with the triangle RST, and the 5 corresponds with that bigger triangle, triangle UVW. The area ratio, though, is going to be different because for our area ratio, we have to take the similarity ratio of 4/5 and we have to square it. We have to remember that we need to square the numerator, the 4, and the denominator, the 5. Well, 4 squared is 16, and 5 squared is 25. So the ratios that we can use to compare the areas are 16 over 25, and for the perimeters, we'll use 4/5. Let's go ahead and start with the perimeters. First, we need to start with the ratio of the perimeters. That's 4:5, where 4 corresponds with the triangle RST, and the 5 corresponds with triangle UVW. Notice that we have the perimeter of 36 feet right here. So the perimeter's 36 feet in the first triangle corresponds with some value P in the second triangle, which I don't know what that is, so that's going to be 36 over P. And now we can go ahead and solve this with cross products. 4 times P equals 5 times 36. That's 4P equals 180. And then divide each side by 4, and you'll get P equals 45. So the perimeter then must be 45 feet. Next, let's go ahead and find the areas. So for the areas, we have to just make sure that we use the area ratio, which is 16 over 25. Well, 16 over 25, I have the area of this first triangle, the 48 feet squared, and we are missing the area of the second triangle. I'm going to just call it A for area. And now we can solve that proportion using cross products. So let's go ahead and take 16 times A equals 25 times 48. That's 16A equals 1,200. Divide by 16 on each side, and you will get A equals 75. So that means that the area is 75, and then don't forget to add in the unit, square feet. This video is getting pretty long, so I'm going to have you try this one as a try now. And then when you hit play, I will have the solution posted. Please pause now. All right, here is your solution. The perimeter of triangle RSTU is 21 centimeters, and the area is 27 centimeters squared. You can see all my work here. I started off by finding the similarity ratio, 4 over 6 was 2/3. Perimeter ratio, we keep it the same, 2 over 3 equals 14 over some P. And for the area ratio, we have to remember to take the similarity ratio of 2/3 and square it. 2 squared over 3 squared makes 4/9. And then again, just line them up. 4 over 9 equals 12 centimeters squared over A. Do our cross products and you'll get 27 centimeters squared. This concludes lesson 7.5. Thanks for watching. Bye.